Okay, we're on 26. I actually did 24 and 25 together in the last video, so now we're on 26. 26 says, a student initially stands on a circular platform that is free to rotate about its center. The student jumps off tangentially, setting the platform spinning. Quantities that are conserved for the platform system as the student jumps off include which of the following? First of all, let's figure out what we're saying. So if the student is here, then tangentially would either be into the board or out of the board. Jumping out like this, that would be radially. So this student is either jumping away from us or jumping toward us. No big deal. If we put the student here, then radially would be out at us, and tangentially would either be to the right or to the left. So in either case, if this student jumps this way or in or out, if this student jumps left or just jumps right, you can have a sense that the platform is going to start spinning, which is 100% appropriate. Thing is, like, if this guy were to jump into the board, he would go into the board, but in order to do that, he'd have to push back on the platform, so it would spin in the opposite direction. So relative to the center, he has momentum one way, really angular momentum one way, and the platform has angular momentum back. And so we definitely have a sense that angular momentum is definitely conserved. Angular momentum is definitely conserved. Let's talk about 3. Is kinetic energy conserved? And the answer is no. Okay, kinetic energy is definitely not conserved because before he jumps off, nobody's moving. After he jumps off, everything is moving. So we gained a ton of energy in our system, so it's not kinetic energy. The one that's really hard to figure out is linear momentum. Is linear momentum conserved? And I know you want to say, yes, linear momentum is always conserved, and that is not actually true. Let's talk about the reasoning here. Angular momentum is conserved if there are no external torques. So in this case, the guy jumping off, he torques the, we'll call it the merry-go-round. He torques the merry-go-round one way, the merry-go-round torques him the other way. All the torques are inside the system. So angular momentum is conserved because there are no external torques. Linear momentum is conserved if there are no external forces. There are no external forces. But this time, there is an external force because the platform is in contact with the ground. He jumps, let's say, into the board. If this was ice, for example, the whole thing would move backward as it spun. But because it's attached to the ground, there is an external force between the merry-go-round and the ground. Therefore, linear momentum, not conserved. I know it's tricky, but that's just what it is. Okay, next one is 28. Oh my god, I feel like we've done this problem a zillion times. Okay, so there's your wall, here's your floor, let's put the ladder on. Now, it's almost always a ladder because you can envision putting a ladder like this. Okay, so a uniform ladder with the way W leans without slipping against the wall makes an angle theta with the floor shown. theta. There is friction between the ladder and the floor, but not between the ladder and the wall, so there's no friction up here. That's cool. The magnitude of the frictional force on the ladder by the floor is. Okay? So the magnitude of the frictional force, so we're looking for the frictional force with the floor. Frictional force with the floor. That's what we're looking for. It can't be the frictional force with the wall because they said there was none. So what we're going to do is we're going to do the same way we attack this problem every time, is we're going to draw our rigid object. And once we have it drawn, we're going to put the forces on it. So here is our rigid object. Okay, I'm going to put the forces on it. So what are some forces? There's the weight. The wall has to push it this way. So this is the weight, that's the W, it weighs W, that's what it says. This is the wall force. I'm going to call it H for horizontal force, so I don't get confused with this one. There's two forces here. This one is the normal force, and this one, so if it could, it would slide out. So we know the frictional force. So this is the frictional force with the floor. That's what we're solving for. So I think this is going to take a net torque statement, a horizontal net force statement, and a vertical net force statement. That's what I'm ready to do. Let's get this party started. So first let's do the torques. I think it's easiest when doing the torques to use the pivot point as the ground. You can use any of the points on the ladder that you like. I'm going to do this one here. So because it's balanced, the net torque is equal to 0. Let's do the torques. Does the weight supply a torque? It absolutely does. Here's your issue. You see this angle here is theta? Well, what's this one here? That's definitely not theta. It's 90 minus theta, true? And so when I think about that, okay, I have to think about, now, one way to do it is to call it 90 minus theta. Another way to do it is to call it phi, and then go from there. I'm going to do that, because I think that's the easiest thing to do. I'm going to call that one phi. And so to express the torque by the W, right, the ladder has length L, for example. So where is the weight? It's L over 2 times the force W times the sine of phi. Now there's another torque up here, right? At the distance L, I have the horizontal H. But what's nice is the angle between those is actually theta. So sine theta. If W were the only force, it would get it to go this way, so that one's positive. H would get it to go this way, so this one's negative. It's 0. So I end up with L over 2 W sine phi is equal to L H sine theta. I'm going to leave that like that for now. Well, we'll get rid of the L's because that's who wants the L's. So I have W over 2 sine phi is equal to H sine theta. Let's leave it like that for now. Let's do the net force statements in the horizontal and vertical and see if we can't make some things come into play a little more. So what do you notice about the net force in the x direction? Obviously 0. And in the x direction, what do we have here? To the right I have H, and to the left I have my frictional force with the floor, which is actually what I'm going to end up looking for. So that's actually good for us. And so I can see that the friction with the floor is equal to the H. So if I knew the H, right? If I knew the H, I could maybe do a little work here and figure that out. Let's do the vertical forces just in case we need them. I'm not sure that we need them, but let's do them anyway. So what about the net force in the y direction? Still 0. The net force is in the y direction. Well, I have the normal force minus the weight. Those happen to balance because they're the only two forces. The normal force is equal to the weight. Now, it doesn't ask us for the normal force. It doesn't give us the coefficient of friction or anything. So I don't really know if we need this. Maybe we could just take this statement here and substitute it in this statement here. And maybe something might come out of that. So I'm going to bring this red one over here and substitute in. So I know that according to what I have over here, W over 2 sine phi is equal to, let's make this substitution right now. Instead of h, I'm going to write the friction with the floor times the sine of theta. And I think that with one trigonometric identity, we could be done with this problem. One thing we remember is that because phi and theta are complements of each other, I think I can say that the sine of phi is actually equal to the cosine of theta. And if I substitute that in there, I end up with w over 2 cosine theta is equal to the frictional force times the sine of theta. And to solve for the frictional force, I end up with w over 2, and this is cool because I have cosine theta divided by sine theta. And so my frictional force, frictional with the floor, is equal to w over 2 cotangent theta, which I'm hoping is an answer. Oh. So I'm looking at the answers here, and it looks like, no wonder you guys had a problem. It looks like the answer is supposed to be D, but when I put it into the thing, it put the W on top and the 2, instead of just the 2 on the bottom, it put the 2 cotangent thing on the bottom. So it looks like 20 is going to need to be edited, but this is the right answer. All right, let's do 30. Okay. Let's get rid of this nonsense. Let's draw this one up. This one's a weird one. So we have the ground here. So there's the ground. We have a pivot point here. And then we have our bar. Which somehow starts off, when we look at it at some angle, theta. Is that cool? So it says, the bar shown is pivoted about one end and is initially at rest in a vertical position. So at one point it was vertical and then it started tilting. The bar is displaced slightly as it falls and it makes an angle theta with the vertical at any given time as shown. Which of the following graphs best represents the bar's angular acceleration as a function of the angle? It's a little bit, this one's a little bit tricky. Okay, this one's a little bit tricky. So what we're going to do is we're going to take a couple different points in time and see if we can't reason this out. So if the bar, let's start here. If the bar were straight up and down, what would we notice about this? Well, we would notice that the Earth is pulling it straight down, but are there any torques on it? It doesn't look like it. So I think in this case, the net torque would be equal to 0, therefore the angular acceleration would be equal to 0. As the bar slightly comes out of, as it comes out like this, now all of a sudden we have a torque on it, right? Now all of a sudden the torque is here. How do you express the torque now? Well, now the torque is equal to, basically it's going to be L over 2 mg sine theta, correct? But what do I notice here? So the mg doesn't change, but what's happening to this angle here? Okay, the angle's getting bigger and bigger. Let's check it over here. If I check it another time, now what do you notice? We still have the same statement here, we still have the same statement, but look at what's happening to this angle. The angle goes from 0 all the way up to, when it comes flat like this. Now what do we notice about our bar? Ooh. Oh, green, what are you doing? So now, what do you notice about your angle? Your angle is 90. Here it's a little less than 90, here it's almost 0. And so over time, if we were to plot this, basically down here, this is your angle. It goes from 0 to 90 degrees. And since we talk about your angular acceleration, net torque is equal to I alpha. The net torque is equal to, in this case, LmG sine theta. If I set these two things equal to each other, I alpha is equal to LmG sine theta. What's happening here?
This is number 17. Number 17 says
We can see that the L, the M, and the G don't change. The I doesn't change, so alpha depends on the sine of theta. So if I plot this, well, what does the sine of theta look like? Starts at 0, it's a maximum here. Is that a sine function? So I'm looking for, in the answers, I'm looking for the graph that looks like that, and I think it should be D as in dog. So that was number 30. Okay? All right, one more. Let's look at 31. Now, before we start on 31, I'm going to tell you, I know there's an answer. And I know the answer is E. Looks like some parabolic increase. But I'm going to be honest with you when I tell you, I've been searching for the answer to this problem in a way that's meaningful to help students understand for like 10 years. And I've never come across an explanation that makes any sense at all. So what we're going to do here is we're going to draw this up. And we're going to see if we can't figure it out. Oh wait, that's not right. A bar at the right is pivoted about one end and is initially at rest in a vertical position. The bar is displaced slightly as it falls, and it makes an angle theta with the vertical at any given time as shown. Which of the following graph best represents the angular velocity as a function of time? Now, I think about this problem, and what we're trying to plot here is the angular velocity as a function of time. So in my head, I know that as it falls, it has to get faster. So my graph has to trend up and to the right. So I'm looking at this, and it can't be B, and it can't be D, right? So it's got to be A, C, or E, all right? But as this falls, I know that it's getting faster, but to what extent I can decide what graph it's going to be. Now, the last graph we had wasn't like angular acceleration versus time, it was angular acceleration versus angle. And so this, I was going to try to take a derivative, and I was going to try to relate it to this. But I can't see a way to get the answer, which is supposedly some sort of parabolic function. Now, why is it parabolic? I don't know. If I look at this over time, this would mean that if I took the derivative of this, that the acceleration was linear with time, but that would mean that the change in position was cubic, but I don't know why that would be cubic. I can't think about it in a kinetic energy sort of way. If we go back and we look, so this is where it started, 0 angular velocity, and then as it falls, I don't know how the angle changes with time. And because I don't know how the angle changes with time, I can't figure out how the velocity changes with time. So I know this is the answer. I would love, and this is for real, and I'm going to put this out to you guys, if somebody could come up with a way, even searching the internet for an answer that makes some sense, that would be great, because I've been searching for years and I got nothing. So it turns out the answer is E. But you guys are going to figure out why. All right, that is enough of that. Thank you guys. If you have any more questions, you let me know.